Welcome everyone, this is a video by the Department of Applied Mechanics, Budapest University of Technology and Economics. Our subject is the dynamics of robot mechanisms, and the topic is the comparison of the feedback controller and the inverse dynamics controller applied for serial robots. Let's consider this RRR 3 degrees of freedom manipulator. There are 3 revolute joints and there are 3 homogeneous prismatic bars with M and L parameters. The equations of motion can be derived easily, for example by the Lagrangian equation of motion. As we see here, we use relative coordinates, which is typical for robots. For example, if we consider the Donald-Hartenberg convention, we realize that also there relative coordinates are used. But the equations of motion could be derived, and this whole study could be accomplished by using absolute coordinate, as we see in the right hand side. For first, we don't apply any controller, we just check the free motion of this triple pendulum, and as we see, the motion is chaotic. However, the total mechanical energy, which is the kinetic energy and the potential function together, is a constant function, as we see here, and the blue curve is the potential function only, and the area between the potential function and the kinetic energy is always the kinetic energy. And this is because the system is conservative. For first, let's try this so-called distributed joint PD controller, which is the abbreviation for proportional feedback controller. The control input is calculated purely based on the positioning error, Q minus Q desired, and the time derivative of the positioning error, Q dot minus Q dot desired. It is very important to mention that the control input is linearly proportional to the error itself. For this 3 degrees of freedom manipulator, our P and D gain matrices are 3 by 3 matrices, and for the sake of simplicity we just try diagonal gain matrices. Let's see how it works. If the desired position or desired configuration is vertical, which is an unstable equilibrium, then the PD controller works nicely. But this is because of the fact that there is no need for any error to keep the system in this vertical position, and we also know that the PD controller does not provide any control input when the error is 0, so therefore this upward vertical equilibrium position can be achieved by any positioning without any positioning error. However, if we consider a horizontal desired configuration, there will be some positioning error. It is because that some joint torques are necessary to hold the system in this desired horizontal configuration. Besides, PD controller generates output torque only if there is a certain positioning error, so therefore it is necessary to have some positioning error to provide the necessary control torques which hold the system in this nearly horizontal configuration. All in all, we can say that this PD controller behaves like a spring damper system. In this video, we see when the desired position or desired configuration is continuously moving. Here it is even more visible that the PD controller behaves like a spring damper system, and the positioning error never disappears. So the idea of the inverse dynamics controller comes into the picture. The control input first is expressed from the equations of motion. So here in the left hand side there is the equations of motion, and on the right hand side the control input is expressed, and the acceleration term here is incorporating the desired acceleration and the PD feedback terms as well. And if we substitute back the control input onto the right hand side, into the right hand side of the equation of motion, we will see that a lot of terms will cancel out, and finally we obtain a stable differential equation for the positioning error. So finally the error will tend to zero as the time goes to infinity. And let's see how it works. If we apply this inverse dynamics controller on our robot and the desired configuration is horizontal, we see that all of the errors are eliminated, and this is because that the equation of motion itself is considered in the control. So the torques which are necessary to hold the system in this horizontal configuration are calculated, and on the top of it there is a PD feedback controller. But if the system is in the desired configuration, then there is no error, there is no PD feedback torques, but the pre-calculated feed-forward terms provide us the necessary torques to hold the system in this horizontal configuration. And let's see what happens if the desired configuration is moving. Our inverse dynamics controller together with the PD feedback works very nicely again. And the question arises, what happens if we switch off our feedback PD controller part? So here only the inverse dynamics part of the controller works, and there is no any feedback. But the error remains zero if the initial conditions are accurate. We mean that the initial position and velocity of the system is according to the desired motion. But what happens if the initial conditions are not accurate and there is no feedback terms? There will be a chaotic motion again because of the lack of feedback terms. So what we can draw as a conclusion is that the feed forward terms are not good enough. Only with a PD controller together, which can be seen in the next slide. So here again there is an initial condition which is not correspondence with the desired configuration, but applying the feedback terms again, so we switch on the feedback controller again, the error decays, and our robot will accurately follow the desired configuration, even if it is moving quickly and there are some accelerations in the desired motion. So that's it for this video. Thank you for your kind attention.